to use this. Nope. I have no idea why this is not working. I'm gonna try it again. There we go. Just a quick outline of my presentation today. I'm gonna give you the objective of this work. Then I'm gonna move on to the criteria we've used to select these materials. Following that, I'm gonna talk a bit about on the fabrication of these epoxy foaming systems. Before I move on to the characterization and evaluation of the resulting foaming systems in terms of their flammability, their thermal conductivity, tensile properties, and water absorption properties. And finally, we're going to have a short look onto how we can implement these as core materials in fiber reinforced composites. So the main objective of this work was to develop novel and multifunctional fiber reinforced composite systems using these epoxy nano-modified foams as a core. So as you can see here, these epoxy foams with the nanoparticles are sandwiched between two phase sheets made out of carbon or glass fabric. So the advantage of these structures is that they're very lightweight, yet they're very strong. They carry several multifunctionalities, and they're typically used to address specific properties in applications such as aerospace, automotive, and construction. Now moving on to the material selection, the scope of this was to identify the optimum and appropriate materials to give us this needed multifunctionality. And more specifically, we were looking into the relevant literature to find out nanoparticles that could enhance the flammability resistance, the electrical conductivity, the thermal conductivity, the mechanical strength, and the water resistance of the resulting foams. And after selecting the applicable materials, we selected two commercially available and common foaming systems with different densities. And we've evaluated the performance of these foams in the presence and absence of the nano-reinforcement selected here. And for each type of property, as you can see here, we've chosen a different enhancements. And in the case of mechanical strength, we actually tried 3 different systems. As you can see here, we're creating this core material that the SEM images demonstrate that results in an open cell structure, which is preferable in aerospace applications. And very quickly, the way we fabricated these epoxy foam systems was to mix the epoxy foam system with the reinforcement. We've stirred it at room temperature, and we've added the hardener before we went ahead and transferred this in the mold. And what is noteworthy here is that we were actually using a sieve to add the nano-reinforcements to break up any aggregates. And actually, we're using a sieve to pour this into a mold, making sure that we eliminate any entrapped gas bubbles that would hinder the homogeneity of the final system. And more specifically, what we've investigated was the flammability resistance when we've used montmorillonite clays. These are nano clays, very typical nano clays used. The thermal conductivity when we've incorporated 2 conductive polymers, graphene nanoplatelets and multi-wall carbon nanotubes. The tensile strength and Young's modulus, of course, when we incorporated, again, graphene and multi-wall CNTs and montmorillonite clays. And finally, the water resistance with aluminium oxides and montmorillonites. Moving on to the morphological characterization, of course, we wanted to investigate the effect of the addition of particles at different concentrations on the morphology of the resulting system. And as you can see here, in the case of multi-wall CNTs that have an average diameter of 10 to 40 nanometers and lengths of 1 to 25 micrometers, we have observed that the diameters of the bubbles we're measuring using SEM appear to increase when we increase the concentration. And the porosity, as expected, drops when we increase the concentration. Now, montmorillonite nanoparticles had a very different effect. We haven't seen a significant change in the morphological properties. As you can see, the average diameters measured were very similar. The porosity, as expected, is also very similar. And finally, when we use the graphene nanoparticles, keep in mind that these are very, very small nanoparticles compared to the previous particles we've checked. The bubble diameters appear to decrease when we increase the concentration of these nanoparticles. When we increase the concentration of these nanoparticles, yes. And finally, the last system we've used were the aluminum oxide nanoparticles. As you can see, the size is also different here. And here we have observed the largest average diameter in the systems we've checked. And again, the bubble diameter and porosity are decreasing when we increase the concentration of aluminum oxide in the epoxy foams. Now, what we have observed, just a quick summary of what we have observed. We haven't observed any significant morphological changes, meaning that we started off with open cell foams, and what we got was open cell foams. The overall diameter distribution ranges between 212 to 340 micrometers. And in the case of graphene and aluminum oxides, we have observed that the bubble diameters decrease. And in contrast, when we incorporated multi-wall CNTs, we've seen that the average droplet diameter actually, bubble diameter, sorry, actually increases. And we have attributed this, we're postulating that this effect is due to the shape and size of the incorporated nanoparticles and their stability on the interface. So what you can see here is the different stability states when we incorporate different particles on an interface. And of course, as you increase the sphericity, you end up with more stable nanoparticles on the interface, absorbed on the interface. Okay, the first property that we wanted to investigate was the flammability resistance. And this is of particular interest in the automotive industry, since these foams can be used as, can be actually used by the automotive industry to, in cars or in seats, etc. And we have seen that increasing the concentration of montmorillonite nanoparticles to 6% weight, we have managed to decrease the burning rate by 13%, which means that indeed incorporating these nanoparticles hinders the burning rate and causes these materials to be more resistant to flames. The next thing we wanted to check was the thermal conductivity of resulting epoxy foams. We wanted to see how they behave under when they're heated, and what we've used was a homemade system consisting of a thermal camera, heating plates, as you can see here. We're holding the sample with these heating plates, and we have an insulated environment. So what we did here was to heat the sample and investigate the temperature along the length and of course along the time of the experiment. And in this case, for this type of experiments, we've used graphene and multiple CNTs, since these are conductive nanoparticles. Okay, so we've ended up with this type of graphs. We have temperature across a certain distance of the sample, and if we zoom in at 10 millimeters from the heating plate, we see that there is a minor increase in the case of the incorporation of 1% multi-wall CNTs. Of course, this is not conclusive yet. We really have to investigate what is happening in terms of the heat capacity of the system. And this is what we're investigating now. But indeed, we see a small increase of the temperature at a constant distance and constant time. Then what we have observed when we compare the plain foams with the foams that had 4% multiple CNTs, we've seen that the knit foams have a better heat capacity. In the case of the 4% CNTs, the rate of loss of temperature to the environment is higher due to the incorporation of the conductive nanoparticles. Thus, we end up with the lower specific heat capacity levels. However, when we compared the two different conductive nanoparticles, we haven't seen any adverse effect. Okay, so moving on to the mechanical properties, and in particular the tensile properties of the samples. We are following an ASTM standard, and we're using a universal universal testing machine with dog bone shaped specimens, and we have tested these to see how they respond in tensile. What we have observed, starting from the two knit systems, we've seen that the system with the highest density, so the 250 system, demonstrates higher tensile strengths and higher Young's modulus. And of course, the bubbles incorporated are larger. Now, when we compare the multiple CNTs with the graphene reinforcements in the 170 epoxy foam system, we've seen that when we were adding graphene nanoparticles at larger concentrations, the tensile strength increased, along with the Young's modulus. And again, this is in line with the increase of the bubble diameter, demonstrating that when we have larger bubbles, reinforced bubbles, we tend to have stronger materials. Okay, the next system we tested was the montmorillonite nanoparticles at different concentrations. We have used the 170 foam to check this, and we have incorporated 4%, 6%, and 10% montmorillonite nanoclays. And what we observe here is actually very interesting. We see a percolation of the enhancement when we use nano-reinforcements. So I'm sure you're familiar with this concept. This concept basically highlights that above a certain percentage, we do not see the enhancement due to the inclusion of nano-reinforcements, because the interactions between these reinforcements become more significant. As you can see here, the 10% montmorillonite has a weaker response, and the 4% actually demonstrates the best tensile strength and the best tensile strength. What was really surprising is that the 10% montmorillonite, even though has quite low tensile strength, demonstrates a higher Young's modulus. Okay, the final property we wanted to investigate, again, in light of the applications we want to use this in, was the water resistance. And we've used aluminium oxide as a reinforcement, ranging at concentrations ranging from 0 to 5%. And what we have done, we have immersed this in these samples of known weight were immersed in water, and measurements were taken at different periods of time. What we have observed is that when we decrease the density of the foaming system, the percentage of the percentage of water absorption increases. And these are the two systems we have investigated, with this system having the higher resistance in water absorption. Okay, now when we've incorporated different concentrations of these aluminum oxide nanoparticles ranging from 0.1 to 1 and then 5%, again, we see that indeed, the water absorption tends to increase compared to the knit system. However, when we incorporated 5% aluminum oxide particles, we've seen a quite important drop in the water absorbed there. Of course, we have to investigate this further, and we're hoping to incorporate a higher amount of concentrations to investigate the percolation here as well. What is noteworthy is that even though the specimens have demonstrated an increase in weight, no swelling was observed, and this led us to conclude that this weight increase is attributed to the water entrapment or within the surface bubbles of the epoxy foam specimens used, since this had some roughness to them. And in general, these hydrophobic foams do not really change when they are exposed to moisture, which is very good when we're dealing with aerospace and structural applications, of course. Okay, as I told you in the beginning, the ultimate goal was to incorporate these foam structures as cores in carbon fiber reinforced polymers and glass fiber reinforced polymers. And this was realized in 2 steps. The first step was to synthesize this foam in a similar manner like I have described earlier. So basically, you choose your reinforcement depending on the property you want to hit. You incorporate it in the structure, and then you cast the structure in a mold. Once this is solidified, you incorporate it as a core material within face sheets made of technical fabrics. And here you can see the carbon fabric and the glass fabric. And what the methodology we've used to incorporate this is something very well known to the industry of fiber reinforced polymers. This was the vacuum assisted hand layup. So basically you cure this under vacuum. And what we have observed that systems reinforced with multi-wall CNTs and graphene have very good affinity with the face sheets. I'm not sure if you can tell, but basically we have managed to incorporate these as cores with the face sheets that you see here in black. These are carbon, and with the glass fiber face sheets that you can see here in white. And this is opening the way to our next experiments that will be to check the enhancement of the, the effect, let's say, of the performance of fiber reinforced polymers when epoxy foams are used as cores. Typically, what we use as cores is aluminium honeycomb or paper, let's say, honeycomb structures. And it will be very interesting to see how these compare to these conventional structures. Okay, and just to conclude my talk today, what we have demonstrated was that the effect of nano-reinforcement size and shape on the morphology of commercial foams has been investigated, and we've actually seen differences in the behavior when we use spherical or oblate nanoparticles. We've seen that the montmorillonite nanoparticles result in inhibiting the burning rate of the reinforced foams, meaning that this could find applications in the aerospace or automotive industry where flame resistance is desired. We've seen that the incorporation of conductive nanoparticles increases the tensile strength and the Young's modulus. And even when nanoparticles are incorporated, we have seen that the tensile properties of epoxy foams tend to increase. And finally, we have successfully prepared carbon and glass fiber reinforced polymers, and these will be used to further evaluate the mechanical, electrical, and thermal properties and check how this would be applicable in construction, automotive, and aerospace industries. So before I finish, please allow me to thank our sponsors, the Research and Innovation Foundation in Cyprus. And of course, thank you for your attention. I'm happy to take any questions if you have.